so before we were doing geometric vectors, which was just a sketch, a graph in any open space. Now we're doing Cartesian vectors, and that's putting those vectors that we drew before and putting them on a Cartesian plane. What a Cartesian plane is, that's just your XY axes that we've done all of our sketches and all of our graphs from. So now the vector is going to have coordinates to go with it. So, here we go. So a position vector. This is a vector whose tail, the dot, is at the origin, and the point would be the head of it. So if we have this as our point, the AB, we'd say like 1, 2 in round brackets. If you say it, and I'll move this, if you say it with square brackets, that now is a notation for a vector. So if you see coordinates with square brackets, it's a vector. All right, now for the unit vector is basically one unit, a unit. It's 1. So if you look here, and I'm going to switch to red, you can see it along here. When you go along the x-axis, so the vector is from tail, and it goes out, it goes only 1 unit. This is your I vector. So it's your x-axis unit vector. And if you went up along the y-axis, so the vector is going up, you only go up to 1 because it's 1 unit. This is your j vector, and then it gets the little hat as well. So j is your unit vector for the y-axis. So for the magnitude of a vector, magnitude means the length of it. Or if we're given the velocity, you'd be finding how long that is. So on a Cartesian plane, if you had your vector as v1, v2, that's still just your x and your y part of your vector, so where it's landing. And if you're a position vector, so you're at the origin, to find the distance, you would square the first one plus the second one, and you'd take the square root. So what are you really just doing here? That's right, Pythagorean theorem. Okay, so for adding vectors, when I did this, essentially all you need to know is this part. When you add the two, all that's doing is adding the first parts, so from your v and from your u, take your x part of it and add those two together, and then take your y parts and add those two together, and that will get your final vector. But to show you, I wanted to show that you could take here and write it as a unit vector. So you take your u1, 0, so that's your unit vector for I, and then 0, u2, which is your unit vector with the y, so that's your j, and written again here. Okay, so these are the same things. And then collecting like terms, you have 2 here with i's. So if you factor out the u1 and the v1, that's your unit vector I, which is just 1, 0. That's what we said that vector was, sketched on the graph. And then if you multiply this into the vector, so here and here, well, this times 1 is just itself, and then times the 0 is 0. And likewise, the same thing's happening with the j, except it's just your y component. And now when you look at this, if you're going to add these two together, if you do this here plus 0, you just end up with what we have. And likewise here and here, you get u2 plus v2. So really, it's really simple. I was just showing you how. Now when you're multiplying, it's essentially just the distributive property again. So you take your k and you multiply it in. So if your original vector was u1, u2, you just take the k and you multiply it by each one. Subtraction of vectors, it's the same thing. Whatever your first one is and your second one, you take the x component of the u and you subtract it from the x component of the v, and likewise with the y components. So if you're looking for this distance where it's not at the origin, you would just take your points. So you'd have your p being x1, y1, and your q being x2, y2. And if you were to find pq, you could actually just subtract. So if you went from p to q, you have to subtract the q from the p to get those coordinates. Are you okay with that? And then you just do the distance formula, which is still just Pythagorean theorem, but you would take this component, square it, plus this component, square it, and then take the square root. So you could have written s as 3i plus 5j, but if we want to write it as a vector, so we're having the vector components. Sorry, that was t. So for s, it is 5i minus 1j. Mean. Just this. How else can we write that? As just an I unit vector. 1, 0. So if we're going to write 5 times that, then your final vector will just be 5, 0 plus 0, -1. And so for the next one, if you have 3 times s, you take your s, which is 5, -1, and you multiply it by 3. And it's essentially just the distributive property. So you would have, what would you finish with? 15, -3. Do it. So what would 2 times s be? 10, minus, what's 4 times t? Okay, careful because it's, okay, so we left the minus there, that's fine. And then what did you say? Good. Sorry, ran out of room. Now if you're going to subtract it, what do we get left with? -2, Good. So I would recommend finding s minus t first and then doing the magnitude of it. So if we did s minus t, we have, which one's s? Scroll up. S, so we have 5 minus 3, so we have 2. And then the next one is -1 minus 5, so we have -6. And what was the equation for the magnitude when you just have the one vector? Perfect. So if that's your diagram, then you have the square root of 2 squared plus -6 squared equals 4 plus 36 equals root of 40. Can we write this in another way? So that would be the other way we could write it. So in this one, we have our 2 vectors here. So we're not from the origin. We're going to do it slightly different. And so if we're going from C to D, D is your second point. So that is your x2, y2, x1, y1. And you're basically just plugging your values in to find the magnitude of it. So we're doing 1 minus 4 squared plus -7 plus 3. Why is it plus 3? We have -3 squared plus -4 squared. So we have 9 plus 16. What's the answer? 25. So the answer is 5.